Hello students, and welcome to a new calculus lesson. This is going to be one of the most amazing parts of your calculus career, and this lesson is going to be about related rates. I'll let you know that this is going to be several videos for 4.2. I would recommend that you actually take about 2 days to cover this material because it's going to take you a while to actually work through these problems. This is going to be a very important lesson for you to master for the free response section of your AP Calculus exam in May. Without further ado, let's get started. So in this first page, we're going to be looking at related rates, and it says implicitly differentiate the following formulas. And what you want to notice is that all those formulas, surface area of a square, volume of a sphere, A is the square root of c squared minus b squared. Those are all very common formulas that you should recall from middle school and geometry. What we want to also notice is that we want to take these derivatives with respect to time. So think back about our last lesson where I kept saying with respect to x, and what we would do. We would do dy dx. Okay, so this is with respect to time. So d whatever dt. Okay, so as I'm going through this, we've got the area here. And so it says A equals 4 pi r squared, the surface area of a sphere. Okay, so we're gonna go, all right, so dA dt, so the derivative of area with respect to time equals, so bring that 2 down, we're gonna get 8 pi r, so 2 minus 1 in the exponent, and then we're gonna get dr dt. So we've got two variables there. Well, we got three variables here. So we've got dA dt, we got r, and we got dr dt. So r stands for our radius. So what does dA dt stand for? Well, that's just going to stand for the rate at which the surface area is going to be changing. So now we want to say, okay, what does dr dt? So it's the change in the radius with respect to time. So it's the rate at which the radius is changing. All right, so let's go ahead and look at this next one here, shall we? So we're trying to find the volume of a sphere. So let's take that derivative. So this is going to be the derivative of the volume with respect to time. Okay, so we're going to bring that 3 down. We're going to multiply it by 4/3. We're going to get 4. Pi is a constant. R, subtract 1 from that exponent. 3 minus 1 is going to give me 2. And then drop that breadcrumb dr dt, that chain rule. Okay, so let's look at these things again. So what does dv dt stand for? Well, that's going to be at which the rate at which the volume is changing. And then for dr dt, what does that stand for? Well, that's going to be exactly as it was before, the rate at which the radius is changing. So now I'm going to move down to here. What you want to notice about this particular equation is that this is probably more well known as the Pythagorean theorem. So you might also recognize this as something like where it says x squared plus y squared equals z squared. Could recognize it as that. And as we're going to take this derivative from what's here, you might also want to say a equals c squared minus b squared to the power of 1/2. So just rewriting that square root like I tend to do. All right, so when we take this derivative, right, when we take that derivative, I'm going to get dA dt equals, we're going to bring that 1/2 down, so 1/2. Now I do want to note that c is going to be a constant, so bring that 1/2 down, and we hold on to the inside, so c squared minus b squared to the negative 1/2. Okay, and we're going to multiply by the derivative of the inside. So c is a constant, so that's 0 minus b squared. So we're going to take that derivative. So bring that 2 down, that's going to be negative 2b. And then we're going to subtract 1 from the exponent, which is going to be 1. And then we have to drop that breadcrumb. So that's going to be dB dt. And of course, if you want to switch this up with the x, the y, and the z, you could definitely do that as well. Okay, so let's just rewrite this real quick because those 2's are going to divide out, and I'm going to get dA dt equals negative b, so that b is going to stay in the numerator, and then I'm going to get the square root of c squared minus b squared in my denominator, and this is still multiplied by dB dt. Okay, so let's kind of write what we're trying to say here. What is dA dt? So we want to write, what does dA dt and dB dt stand for? What are those rates? Well, those are just the rates at which, again, it's for a triangle. If we're looking at some sort of triangle that's happening, is the rate at which A and B are changing. So now we're going to go down here to the volume of a cylinder. So volume of a cylinder, let's see. So R is going to be a constant here. So we just got a constant multiple. So let's just take that derivative with implicit differentiation. So I'm going to get dV dt equals, so it's just a constant times the height. So the constant is going to be pi r squared, because that's a constant multiple. And the derivative of h, well, that's just 1 times dh dt. So what does dV dt stand for? Well, that's just going to be the rate at which the volume of this cylinder is going to be changing. Think of something like a soda can or Pringles can. So now what does dH dt stand for? Well, dH dt is going to be the rate at which our height is changing. So now we've got a couple more to go. Again, it's another reference to a triangle here. Okay, so one thing that you do want to just kind of think about, we do have this constant multiple of 1 over 15x. And again, it may just be a separate problem with different values, but we're just throwing values in here so you can kind of take a look at it. We're taking this with respect to time again, so not dx, okay? We're not changing, we're not looking at the change with respect to x. What you really want to think about is, all right, if a certain side is expanding at a certain rate, how does that change the area? How does that change the volume of these certain shapes, okay? So what's the derivative of cosine of theta? Well, that's going to get us first negative sine theta, and then derivative of theta is going to be d theta dt. All right, and so what is that going to get us? Well, that's going to get us 1 over 15 dx dt. Again, because we're not going with respect to x, we're going with respect to time. So here, when I'm looking at this d theta dt, well, that's the rate at which the angle is changing with respect to time. Okay, so then what does dx dt stand for here? Well, that's going to be the rate at which that horizontal line, that x, is changing with respect to time. And one thing you always want to consider as things are changing with respect to time, think about things like miles per hour. That is the distance in miles with respect to hours. So that's how we're looking at these rates. All right, one more formula to kind of look at. We're going to look at the volume of a cone here. And one thing that you want to notice here is that we are multiplying. So we're going to have to use that product rule. So as I'm looking at this, I want to get dV dt equals, okay, so the derivative of the first, I'm going to bring that 2 down. So I'm going to get 2/3 pi r squared times, actually, no, that's a little bit off. So 2/3 pi r, and then I'm going to multiply it times h, and then I'm going to get dr dt. Okay, so that's the derivative of the radius with respect to time, and then plus the first, so 1/3 pi r squared times the derivative of h, which is dh dt. So what do all of these mean? So we've got dv dt, right? We've got dr dt, and we have dh dt. Well, just like you've seen from all of the other examples that we have above, we're looking at the rate at which the volume is changing, the rate at which the radius is changing, the rate at which the height is changing with respect to time. So if all three of those things are changing, we can see what the particular radius is, we can see what the particular rates are, and we just need to solve for these very simple formulas from there. All right, so that's going to conclude this video. You don't actually need to memorize any of these formulas, okay? Don't worry if you don't know what the formula is for the volume of a sphere or a cylinder, okay? You really should know the Pythagorean theorem if you are in calculus, okay? So you do want to know how the sides of a right triangle are related. So if you are in calculus, you should know that. You should also know all your trig formulas, how you would work with those in certain cases. All right, but everything else from geometry you really don't need to have memorized, because when it comes down to like a calculus exam, you're going to actually be given those formulas as you need them, okay? What's more important is that you know how to do everything here on the right, taking that implicit differentiation with respect to time. That's what's going to actually get you the knowledge, get you to where you need to go on this AP Calculus exam, okay? So if you do need any help reviewing how to do any of these implicit derivatives, please let me know. I'm Mr. Hernandez, and this was Mr. Hernandez Teaches.